Hello everyone. So in this session, now we'll be discussing about shift register. Let me recall, in the previous session I was talking about a register. So what is a register? It's a array of flip-flops which stores multiple bits. So a flip-flop only stores a single bit. So that's the reason for storing multiple bits we have discussed something called registers. So registers are nothing but array of flip-flops which can be stored multiple bits. So let us discuss once again the types of shift registers. So a register can be used for multiple operations. So one of the operation is shifting operation. I can shift the data bits or I can load the data bits. So based on that we are discussing in the today's session the types of shift register. So we'll understand SISO, it is nothing but serial in, serial out shift register. So we have another serial in, parallel output. So we call it as SIPO, and we have PIPO, this is parallel in and parallel out shift register, and we have PISO, which is parallel in and serial out shift register. So today in this session I will be discussing how this registers operates and how the bits are shifted either serially or parallelly. So let us discuss one by one these registers. So let me give the overview of all these registers. So you can just see SISO stands for serial in, serial out. So the bits are sent serially. So serial transmission in the sense I need to send the bits one bit at a time, one after the other. So when I start transmitting this bit, example 10110, so this I will start with LSB and this is MSB. So one bit after the other bit at the output side the bits are sent. So this is nothing but serial in, serial out. The next case is serial in, parallel out. So I will be sending my data, no doubt I will be sending in serial fashion, but I want my data at once or parallelly. So I will be taking all this data outside at once, that is called as parallel data, parallel output. So the third one is PISO, parallel in, serial out. So parallelly I will be loading my data, but I need my data output as serial fashion. So one bit at a time. So last one is parallel in, parallel out, where I will be discussing about all the inputs are sent parallel and simultaneously we are taking those inputs out at the output side parallelly. So let us discuss the internal block diagram, the structure, circuit of all these four with their functionality. So let me start with serial in, serial out. So this shift register can be built either using JK flip-flop, SR flip-flop or D flip-flop. Taken an example here using JK. So whatever the bits I am sending here, J and K, and you can see I am using 4 flip-flops here. So each flip-flop will store 1 bit. So 4 flip-flops has a capacity of storing only 4 bit. Suppose I want 8 bit, I need 8 flip-flops here. So I am applying clock here. This is bubble represents a negative clock. So with respect to negative edge, all this flip-flop will respond. You can just see the first flip-flop output is connected as the input to the second. Similarly, from second output is connected to the input of third. Third output is connected to the input of 4. So this is how serially it is connected. So I am going to apply my data inputs to J and K here. You can see with respect to clock negative edge. So we have taken the clock time as A, this is clock cycle A, B, C and D. So we are providing the inputs here. Example, if I give J as 1 and K as 0, 1 and 0. This 1 and 0, J is 1 and K is 0 is nothing but set condition. So that means to say that my output of the first flip-flop is logic 1. So this 1 has to be transferred to the next flip-flop. When this will be transferred, so when my J and K 1 and 0, the next clock transition my Q is 1. So initially my J and K was 0, so no change condition. So when my J has become 1, K has become 0, so my flip-flop output will be in the next clock pulse it will be logic I. So this pulse or this output from the first has to be shifted to the second. So this will be shifted in the next clock pulse, this one will be shifted. Similarly, next clock pulse, this one will shift here. So each clock pulses, this one output from Q is connected to J, this will be shifted in serial way. So finally I am going to get the output over here. To send all this 4 bits, how many pulses you require? Yes, we require 4 clock pulse to get all the bits out of this register. So you can just see the truth table here. Initially assume that all the flip-flops are containing 0 or cleared or reset to 0. Applying clock pulse, when I give suppose input has 1, so next clock pulse this 1 will be shifted to the first flip-flop, and the corresponding registers, the corresponding flip-flops will be holding 0. So unless a next pulse comes, next clock pulse, since I am giving 0 here, next clock pulse this 1 will be shifted to the second, 0 will be shifted to the first. In the next coming clock pulses, this 1 will be shifted to the third, then 0 to second, 0 to 1. Similarly, all the bits are shifted. You require 4 clock pulses to shift the bits. So this is what is given. Flip-flop Q has serial data input 0, R has input 0, S and T all initially will have 0. So add the clock trigger, since the clock has negative edge. So we can see at the clock edge with the serial data input is moving. So serially you will get 0 0 1 0, next 0 1 0, then this 0 1 0 0 is shifted in the next clock pulse. So each time 1 bit will be shifted to the right. So either I can shift this bit right or I can shift this bit left. So if I am shifting from right, the last, when it moves to the last flip-flop, the previous data will be lost. So the right end most will be lost, previous stored data. So similarly, the previous stored data will be shifted and the new coming bits are transferred to each flip-flop. So to transfer this bits, so each clock pulse 1 bit at a time, so we require 4 clock pulses to complete the entire cycle. So if you apply again the next clock pulse, the last LSB part will be shifted out or the data will be lost. So you can just see here the clock timing. So Q1 is shifted here, the next it is shifted here, next it is shifted here. After the 4 clock pulse, it is 0, it is lost. So I am transferring now 0 1 0 1. So 1 has been shifted, next 0 is shifted, next 1 is shifted. So 4 clock pulses will be completing this 1 2 3 4 will be completing this cycle. So this 7491 is a shift register, an IC which is an 8-bit shift register which is made up of SR flip-flop with negative edge clock triggering, and we have 2 outputs and the clock is connected to all the flip-flops. Since it is 8-bit shift register, we require 8 flip-flops and all flip-flops are tied to a single clock. So there is another control over A and B here. You just see this A and B. So I can either send R or I can send S. I can reset or inhibit or I can set. Suppose I am giving my output of this NAND gate is 1. So if this is 1, 0 means it is in set condition. I am transferring 0. If the output of NAND gate is 0, so I will be transferring 1, logic 1 to this shift register. Either I can transfer logic 0 or logic 1 to this shift register with the help of this NAND gate. So NAND gate acts as a controlling ear to send 0 or 1 to this S and R. So 7491 register has 8 RS flip-flops, connected to provide a serial input as well as serial output. The clock input is negative edge triggering, negative edge sensitive. The applied clock signal is passed through an inverter. So data will be shifted on the positive edge of the input clock pulse. So why positive edge? Because it is sent through inverter. So since it is bubbled here, so inverter and inverted, so it becomes cancel and it will be positive edge triggering. So data level, the inverter connected is between R and S on the first flip flop means that the circuit function as D flip flop. So as I said, I can use for shift register either D, RS, JK. Suppose I want to connect SR as a D, I will use an inverter. That is the conversion of SR to D. Data level is complemented by NAND gate. So whatever the input I am giving, based on the NAND gate output, either one of the output is 0 or 1, then it is fed to the flip flop. So next concept is serial in, parallel out. So serial in, parallel out, we have the connections like this. This is the circuit diagram or logical diagram, I can say, to send my bit serial and I take the bit parallel. So this functional diagram or logical diagram is made up of SR flip flop. So which is holding 8 flip flops. 8 flip flops means 8 bits. So we have a control logic here to either make R0 or make S1. So I can inhibit the data stream or I can move the logic 1 into this. So there is a clock over here and there is a clear. So what is this clear input? So clear input is nothing but which it is also called as asynchronous input. Irrespective of clock, anytime I can disable or clear or reset this flip flop. So clearing in the sense I am making this individual flip flop 0. It holds 0 irrespective of whether clock is high or low, whatever may be the input. So the flip flops are cleared. So we call it as asynchronous input. It is not in synchronous fashion. Anytime I can make these flip flops cleared or I can clear all these flip flops through this asynchronous input. So you can just see this clear signal is connected through an bubbled inverter which is connected to an input to the flip flop. So this is asynchronous input and all the clock output is connected to flip flop input to all the flip flops through this common line. So common clock is fed for all the flip flops and the output of first is connected as input to the second. So we are sending my data through the signal A or B. Either I can send 1 or I can send 0. Based on this NAND gate output, I will be sending this. So what is this parallel output? Since in serial output, I need to wait for 4 clock pulses in case of 4-bit register to get my data. Suppose I want my data immediately, I don't want to wait till the end of the clock pulses. So immediately I can take data from each flip flop. So that is called as parallel. You can just see here the output of this flip flop, first flip flop is taken here. QA, QB, QC, QD like this H. So all the data I can take from each flip flop parallelly. Parallelly in the sense simultaneously. Serially I am sending this. So in the next you will get immediately the output. So whatever the previous stored, the same thing you will get. Suppose I have fed here 1. So previous state for all these flip flops are 0. So in the next clock pulse I will be getting output side 1, 0, 0, 0, 0, 0 and 0. Suppose in the next clock pulse this 1 will be shifted here. So I will get my outputs, assume that the first flip flop has got 0, I will get 0, 1, 0, 0, 0. This is how I can retrieve data immediately. So that is called as parallel output. You can just see the waveform for entering data. So I am entering 0, 0, 1, 0, 0, 1 into the register. So which is in serial mode. So whenever the clear is low, you can just see clear is low. So if clear is low, all of my flip flops are cleared. So you will get 0 0 0 at the output of all the flip flops. So whenever I make clear I, then only your flip flop operates normally. So whenever I am feeding, suppose I am feeding my data here A, and I am giving another input called as control input. So whenever a data input is given, when control signal is low, nothing is transferred. When control signal is high and my data is in, so in the next clock pulse, so once I sending this data, when my control signal is high, in the next clock pulse QA, so the data is transferred. So this one is transferred in the next cycle and next cycle, this cycle. So actually we are taking all this output in parallelly. So we are getting 0 0 1 0 1 1 0 simultaneously. So if I am shifting right one bit at a time, it is serial out. So if I am taking immediately at these pulses, I will be getting output. So you can just see this A and B, A acts as a data signal, B acts as a control signal. So I can control this entire flip flop by making B high. So QA, QB, QC initially will be 0. So wherein I should get at the output side 0 0 1 0 1 0 0 0 1 0 1 1 0 0 simultaneously. So when at the end of k clock pulse. So why at the end of k clock pulse I will be getting this? So because I have inhibited here and I have made control signal, this output, this input what I am given here will appear in the next pulses. So on the next 4 clock pulses you are getting the output parallelly. So another concept over here is parallel in, parallel out. So I am sending my data. So the connections or the logical diagram changes here. So I am sending my data parallelly. So I am using here D flip flop for this register. So D1, D2, D3, D4, D5, we have here 5 flip flops, it is 5 bit shifting. I can feed this, since you know what is the function of D flip flop just stores the data. So I am storing the data, next clock pulse I will be sending the same thing at the output side. So first clock pulse where I am feeding all data simultaneously to each of the flip flop. Whenever the clock edge occurs here, so you can see here clock is connected through inverter. So clock edge occurs here with respect to negative clock, right. So this flip flop respond, all the flip flops are connected simultaneously. So the input given to the D first flip flop, second and third appears at the output, the next clock transition. So anytime I can clear all of this flip flop by giving an asynchronous input. As I said, it is nothing but clear. So we have an option here, a clear, which is connected to clear input of all the flip flop. Anytime I can clear, suppose I have stored logic 1 in particular flip flop, I need to remove it, then I apply clear immediately, which clears the flip flop. So parallel in, parallel out shift register accepts input in parallel, and in the next negative transition, clock transition, all this parallel data will be shifted out. Suppose I am taking 6 bits, then 6 bits at a time has to be loaded in the register in parallel, and all the 6 bits are available parallelly at the output side from Q1 to Q6. So since this type of register is used to store data, it is also called as data latch. I can store, or suppose I want to transfer the next clock edge, it will be transferred. So the clear input is asynchronous, it can be done anytime. Next we will be discussing parallel in, serial out. So here if you can see this logical diagram, I need to discuss about what that additional control circuits have been connected to this flip-flops. Okay, so let me analyze this once again about this additional circuits introduced in this shift register. So you can see we have sets of 2 AND gates and 1 NOR gate. So this NOR gate is connected to flip-flop. So this, since we are using it S R with inverter to S, and of course there will be a clock here. Similarly, the clock is connected to next. Similar fashion for all flip-flops, I will be using this control circuitry, additional circuitry with 2 AND gate and 1 NOR gate. So here this AND gate is one of the input is connected to serial input. So the next is connected to, so similarly it is connected to so this is connected to output, from output it is connected to the next one. So here we have the input here, and the next part is connected to mode control. So what I am doing in this mode control, here it is connected. So this portion is connected once again to mode control. So I am loading my inputs here. So similarly I am loading my inputs here. So serial input is coming to first AND gate. Mode control we have 0 and 1 option, so which is connected to this AND gate. So similarly here we are doing 2 operations here. One is the, since it is parallel in, serial out. So parallelly I am sending the data, then I am taking this output serially. So parallel in the sense I need to first load my data into this 4 flip-flops, say RS, Q, so I need to load data here parallelly. So first option, loading option, load and then store. So I will be storing this. So when I want to shift this, my mode has to be changed. So shifting from loading and then shifting. So mode control has to be shifted or it has to be changed. So we are using one control signal. Whenever there is a mode control 0 or 1, based on that I am going to load or shift. So you can see here, so when my mode is 0, this will become 1 and this is 0. So this is 0 in the sense this particular gate will be low and this particular gate will be high. So I make suppose mode control 1 and this is 0 and this will become 1 and this gate will be enabled and this gate will be disabled. So either one of this AND gate is enabled and other AND gate is disabled. by giving the signal over here. So when my mode is 1, so here it is 0, 1, so 1 in the sense this gate is enabled. So if this gate enabled, whatever the clock, the signal coming from here will be sent here. So that is stored here. Similarly here, this is stored. Suppose I am sending 1, 0, so this 1, 0 is stored here. So this is nothing but loading. So now note that only this portion is figured out and this portion is carrying the signal and it is stored here. So unless until I make the transition, clock transition, or I make this to move, I should make this control 0. When this is 0 and this is 1, and this gate will be disabled and this gate is enabled. If this gate is enabled, whatever the serial input I am giving here, that is loaded, then it is transferred. So I am doing this parallel in, then this will be sent in the next clock transition, this will be sent to the next flip flop. So you can just see in this diagram, there is a serial input connection and there is a mode control connection. This serial input connection is connected to the first AND gate, and as well the mode connection is given. The second AND gate consists of mode connection as well as data input, parallel input connection. So at a time one of this gate will be enabled. When this one of the gate is enabled, so output of this NOR gate is low. So once again it is connected to the flip flop. Either I can use SR flip flop or I can use D flip flop. So this is how I can send this in the next clock transition. The output of this is connected as a serial input of the second. So serially I am taking this, even though it is loaded, this A is loaded here, B is loaded here, C and D is loaded here, but serially I need to take this, then when next clock pulse, this transition is shifted here. So it's going to shift in with respect to mode control. So either I can do right shift or I can do left shift. So this right shift and left shift option can be done using this additional control circuitry. In this additional control circuitry, you can see this gate output is connected here, output of this gate is connected to clock. So either I can do right shift or I can do left shift by giving the mode control here. So this is nothing but parallel in, serial out. So two clock inputs, clock 1, right shift, left shift. We have serial input, we have mode control. So either of the gates will be high or low based on what mode I am giving. In mode control, the line I makes AND gate on the right input of the NOR gate, which will be enabled, while the left AND gate is disabled. The inputs will be then loaded into the register on the negative transition of the clock. So if the mode control is 0, the AND gate on the right side of the NOR gate is disabled while the left AND is enabled. The next clock transition, this data bit is entered serially into the register. At the first flip flop of QA, you will get the output, and each stored bit is shifted one bit at a time to the towards right. So this is nothing but serial input of the data in write operation. So let us discuss another concept where a concept called universal shift register. This universal shift register does all operations. So it is out of the box. I am just giving the how exactly it is operating. Either I can make this serial in, serial out, parallel in, parallel out, parallel in, serial out, serial in, serial out. So all possible 4 possible combinations can be generated from this IC. So this is called as universal shift register. You can just see there is a 4 flip flops over here which does this, and there is a control circuitry. Either this can be operated in parallel mode or it can be operated in serial mode. So we have mode control inputs here, we have serial shift right, shift left operation here, and we have clock and clear asynchronous input, serial input for left shift, serial input for right shift. Through this AND gates and OR gate control circuitry, I will be using any of this combinations. So we have this IC which does all this 4 operations. So you can see this IC 74195 universal shift register, which is of 16 pin IC. We have clear asynchronous input, serial data write input. So explicitly we have a pin for right shifting the data, and we have parallel output PA, B, C and D represents parallel output. We have serial data that can be shift left side, and there is a ground connection here. We have a mode control S0 and S1 which is of 2 bits. So out of these 2 bits I can do 4 different operations by giving this S0 and S1 001 and 1011. If my S0, S1 both are of 0, so I can hold the bits. The register is in hold state, it is acting like a latch which stores the bit. Suppose I want to do shift right operation, so 0 and 1, shift to right, I can do right operation. So I need to give this mode selection as 0 and 1. So if I give 1 and 0, I need to do left operation. So suppose I want to do parallel mode operation, then I will be giving 1 and 1. So we have clock here and we have parallel data output. So we have VCC here. So this is nothing but universal shift register IC. So before I conclude, I just want to summarize what is the advantage of parallel output compared to serial, and what exactly where exactly I can use this shift register, what kind of applications. So let me discuss the applications of it. So as I discussed, SI, SO, I will take 4 bits. Consider D flip flop, Q0, Q1, Q2, Q3. So D flip flops, and we have a clock which is connected. I will take a simple positive edge triggering and I am giving input here. Suppose I want to shift the bits like this. So this is my data, I need to send this through shift register. So first I will start with LSB. So 1 will be sent here. So initially I write my output as Q3, Q2, Q1, Q0. So initially my flip flop here holds 0. So next clock pulse, this 0, so I will write this as Q0, Q1, Q2, Q3. So next clock pulse, when the clock is applied, this 1 is sent to Q0. So this will be there inside this flip flop. This will come out of this flip flop only at the next clock pulse. So I am sending this in the next clock pulse, you will get 1, the rest all will be zeros. So next this 1 has come here, now I am sending the next 1 here. So this 1 will be moving here. So next clock pulse, this 1 of Q0 is sent to Q2 and this 1 will appear here. Similarly, next clock pulse, so I am sending 0. Next clock pulse, I am sending 1. So, this 1011 will appear after 4 clock pulses. So, next clock pulse all this will come out. So, this last bit will be lost, still you want to shift. So, this is in serial fashion. Suppose I have data like this 0011. So, if 0011 I do left shift operation. So, this is nothing but 6 in binary in 60011. So, in decimal I will be representing this as 6. Suppose I do left shifting, I will get 0110. So, what is this 0110? So, it is nothing but 4 plus 2, sorry, this is 3 and this will be 6. 2 plus 1, it is 3 in decimal. When I do left shifting, so this 1 will appear here, this 1 will be appearing here, this is 6. So, your data has been doubled here. So, it is nothing but 3 2s are 6. So, left shift operation you are doing multiplication. Suppose I do the same thing here, right shift, so I will get this. So, it is nothing but 6 divided by 2. So, you are getting 3. So, left shift operation, it is nothing but shifting towards left. So, you are getting your data is multiplied. Shifting towards right, so your data will be divided. So, basically this shifting right or left operations are used in multiplication and division. So, multiplication and divisional circuit is made up of shift registers. So, in your CPU multiple operations, integer operations, arithmetic operations are performed using this shift registers. Suppose the same data I need to wait to get this for 4 clock pulses. What if I take my data here, so suppose I am taking my data from each output of the flip flop. I need not wait for so many clock pulses to get the bits. So, immediately the 1 is sent. So, whatever the data is transferred, immediately I am going to get this. So, how many clock pulses you require to get this data? So, you require initially it will be 0. So, when I load the data bits, so immediately in the next clock pulse parallelly I can get, so whatever it is stored here, I need not wait for 4 clock pulses. So, that is the advantage of parallel shift register. So, serial shift registers has got advantage, right shift, left shift will be using in arithmetic operations. For parallel fast transmission in communication circuits wherein I need to send the data immediately, so then I can use parallel transmission. So, many of the communication field will be using serial transmission as well parallel transmission. Based on that, the circuits are designed for transmitting data. With this, I just summarize now the types of shift register what we discussed in the class, this session, and there are multiple ICs available for 8-bit, 16-bit shift register. Based on the applications, we are going to use those ICs. So, we have 4 shift registers: serial in, serial out, serial in, parallel out, parallel in, serial out and parallel in, parallel out. So, we have used JK flip flop, or I can use D or SR. So, if I am using SR, it can be treated as D by using an inverter there. So, each clock pulse the bits get shifted, and you can see the timing diagram where how many clock pulses it required to move the data. There is a shift register, so 7491, which is an 8-bit shift register. I can send this 8-bit serially. We have serial in parallel out. This serial in parallel out is once again controlled by a circuitry NAND gate. So I am sending the signal from through NAND gate, and parallelly I can take the data out, then waveform entering from this register. So how the parallel data will be taken, parallel in parallel out. So multiple inputs are given simultaneously and the clock is applied. So whenever the clock appears, all the data are taken out. So parallel in, serial out. So we have an additional circuitry wherein I will be doing your two operation, that is loading and then store and then shift operation. So loading operation is done first and the second operation will be shifting. So load and shift. For loading, one of the gate will be enabled. For shifting, the other gate is enabled, since we have two AND gates, right and left AND gate. So based on what operation, always we need to do load first the data and then I need to shift it out. So load, this is done through mode control operation. We have a universal shift register which does all these 4 operations. So this shift register has got mode control. With the help of this mode control, I can do all 4 operations. So we can take the output data parallelly, we can give the input data parallelly, as well I can give the data serially. With this I conclude so types of shift register and its applications and its significance of universal shift register. Thank you.